we made it past the main group and periodicity trends there, so we'll talk about the D block, the transition metals. And so I will ask you at some point what the D block elements are. I had to memorize this as a freshman, so shall you. Well, it won't be like on the exam, but you should know it. So we have scandium, titanium, vanadium. So vanadium is in group 5 because we have SM elements over here. So this is the D block. So this is group 3, 4, 5. So group 5. And then we have chromium, manganese, iron, cobalt, nickel, copper, and zinc. So those are the first row elements. So these are the 3D elements. Then we have 4D, 5D. So below scandium, we have yttrium. Then we have lanthanum, which is technically lanthanide, but we'll just kind of put it in here for now. And then we have titanium, zirconium, hafnium, niobium, tantalum. In Greek mythology, Niobe is the daughter of Tantalus. Molybdenum, tungsten, technetium, which is radioactive, rhenium, ruthenium, osmium, rhodium, iridium, palladium, platinum, silver, gold, cadmium, mercury. Okay, so that's the D block, 3D, 4D, and 5D. There are 30 elements here, so there's 10 rows, and then we go up to group 12, right, over here. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's the D block. So these are all metals. That's why they're called transition metals. All metallic, all conductive. OK. So now that we have the D block, let's talk a little bit more about trends. So trends within the D block. If you remember, I'll show you the slide on Friday, but if you remember the ionization energy plots, we were going higher ionization energy as we went across the period. In the case of the D block, it actually kind of flattens out. So the D orbitals are different than the S and P, and you know how far they extend out. And then so they're all relatively flat going across the period. So yeah, within the same row, they're all quite similar. There are some differences as you add more electrons, or as you change your Z effective. So as we go across, we get smaller, but then we get bigger because then we have electron-electron repulsion within the D orbitals. But I'll show you a slide of that. OK, so down the group, 3D is very versus 4D, 5D. The bonding is actually quite different here. And the reason has to do with the nature of the 3D versus the 4D or 5D orbitals. So if we were to draw, let's say here's a 3D orbital. So here's a 3D. The 4s orbital actually extends out much further. Here's the 4s orbital. So the 4s orbital is further away than where the d orbital reaches. In contrast, if you think about 4D, 5D, orbitals get bigger. Now the 4D and 5D orbitals are shielded by the 3D orbitals, so they're bigger as well because of that. Here's 4D, 5D. And then so when we draw the 5s, 6s orbitals in comparison, they don't extend out as far. So the upshot of this difference in how far our orbitals reach is that 4D, 5D transition metals form stronger bonds. The 3D elements. And that's because if you want to think about bonding between the d orbitals, because right, that's where our valence electrons are, the d orbitals extend out further so they can participate more in bonding than the 3D, which is shielded by that 4s orbital. So that's a key difference. All right. So these are kind of trends. And then one more trend is that the 5D elements don't go as big in size, similar in size, because due to the lanthanide contraction. So here's my D block. You would maybe expect that because we're getting to bigger shells, the 5D should be bigger than the 4D. But here, for lanthanum, I've drawn lanthanum, that's where the lanthanides are. So we're filling in a bunch of F orbitals in between, and we're adding a bunch more protons to our nuclei. And because F orbitals shield more poorly than D orbitals, then we experience that contraction. So similar to what we saw before with the P block. OK, so those are our overall trends. Keep this in mind. So I'll have video 2 next.